Welcome to the ninth lecture of Logic and Distributed Control System. Today we are going to discuss about the register basics, which will be helpful to understand the further programming strategy of PLC. So today the objectives are, at the end of this chapter you will able to list the 5 common types of PLC registers, describe the function of each of the 5 register types, describe how each of the 5 common types of PLC registers is used in PLC operations. So as introduction, it is now time to move on to the timers and counters. Two core functions are available with all PLCs. So till now we have seen using contacts and coils how we can develop the PLC logic and we can implement it using ladder diagram. Now we are going to move to use the timers and counters. These are the two core functions are available with all PLCs. But before we do so, it is best to preface our study with an introduction to registers. Registers are memory locations that provide temporary storage of data, instruction, information, and what is particularly relevant numerical values associated with timers and counters. The register, as a register basics, with the PLC CPU, registers are found in two locations. The microprocessor has internal registers, and most of which are not directly accessible by the user. These registers may be 4, 8, 16 or 32 bits wide depending on the microprocessor, help the control and arithmetic and logic units within the processor to carry out their task. Accumulator registers, data registers, index registers, condition code registers, scratch pad registers and instruction registers all work to temporarily store data, which in turn is used to facilitate the carrying out of program functions. In addition to these internal registers, the CPU's RAM also contains slots that are designated to hold variable information. These locations or addresses become external registers. Throughout this discussion, we assume these registers are 16-bit wide. So basically, we are interested to know these external registers. So throughout this discussion means throughout this course, if somewhere we are using the registers, then by default you can assume that we are actually considering the registers which are 16 bits wide. Each bit location in a register contains either a 1 or 0. So you can observe registers contains on a video terminal terminal units by calling up the register on a keyboard. Means if you want to know that what are the register contents, then video display terminal units are there. By calling up that particular registers through a keyboard, you can observe the contents of the registers. Depending on your PLC capabilities, you may choose to print the register values based on one or more different numbering system like decimal, binary, hexadecimal or ASCII. Registers are usually designated using prefixes followed by numbers, as in the case of this chapter, that is HR 256 represents holding registers. HR means holding register 256. OG2 represents output group register number 2. In other system, a certain numerical series of addresses may be assigned to a specific task or function. One model of PLC has register addresses 901 through 930 assigned to timers and counters only. So for the timers and counters, we will see that their format requires the registers. So maybe some PLCs you will find that 901 to 9030 will be assigned to timers and counters only to access the registers. It is important to determine the functions for the addresses of your PLC registers from its operational manual. But at this point we are interested to know that in a PLC how we can do the IO addressing. So here we want to examine module IO addressing. In PLC, IO modules along with the processor module and power supply sit in a chassis, a physical hardware assembly. The IO modules are actually placed in a IO rack. Each module in turn consists of IO groups made up of a set of terminals. The terminals are used for making field varying connections. In sum, we have PLC with IO module consisting of groups of terminals. The location of an input or output terminal within a module group within a rack will determine a device address. Each input and output device must have an address. So here the pictorial representation has been shown. We can see that the individual modules like power supply, processor, output module, input module are kept in a chassis, and you see the group has been made with the input or output terminals, and which are the chassis are placed in a rack. So now the typical addressing format we will discuss. The addressing format that is given by Allen Bradley consists of 5 levels of hierarchy, starting at the top with a file type and descending to a terminal number. Specifically, a file type designates the input or output module. So it will be either I, start with either I or O. So I for input, O for output. A file number specifies which particular IO module input or output. A rack number determines which rack the module sits in. A group is a set of terminals within a rack. Typically there would be 8 groups in rack, that is 0 to 7. The terminal number is the bit address for a particular terminal input or output. Let us see the addressing module. Here you see the first O designates the file type. O indicates it is output. Then another 0 we can see, that is the file number. Then this symbol represents the file delimiter. Then here 0 represents the rack number. Then 1, it could be in between 0 to 7, that is group. 8 groups in a rack. Then bit delimiter, and then 00, that is terminal number, which is the bit addresses. Here some typical example has been given, that is suppose I1, then delimiter 27, then delimiter 17, that is 17. So then I indicates input, then file number 1, rack number 2, group number 7, and bit number 17. So like that the addressing scheme will be there to identify a particular input or output in a PLC. Now we are interested with the 3 basic registers, what it is known as holding registers. Then input registers, they may be single and group, and output registers, they may be single and group. So these are the 5 types basically. So holding registers, then single and group input registers. So another is single and group output registers. Now here we can see that how the PLC registers, that is holding register, input and output registers are sitting. So here you can see that input registers will be 8 to 12 typically. Then in between input registers and output registers, you can see the holding registers are sitting, that is working or holding registers, they may be 100 to 1000 typically, and the output registers they are in a number of 8 to 12 typically. So now here we can see that from the structure, the holding registers cannot be accessed directly. So but the input registers and output registers can be accessed directly through the input and outputs. Let us understand what the functions of holding registers are. A holding or working registers holds the contents of a calculation, arithmetic or logic. That is, conceptually it is in the middle of the CPU. The holding register is not directly accessible to inputs or outputs. Input and output registers, they may be single or group, interface the holding registers contents to the outside world. Single data signal data from the specific input device is first deposited in the form of zeros and ones in an input registers. It may then be manipulated by the microprocessor and the results sent to the holding register. Conversely, before the contents of the holding registers can affect the output device, they are transferred to an output register. The output registers of zeros and ones drive output interface devices such as opto-isolators. Now here we can see how the holding registers are useful in arithmetic operation, which we will discuss in details later on. Now here you can see, suppose two operands we want to add, and the results of the addition will be stored in a register. So now here you can see operand 1 is stored at HR75 and operand 2 is saved in another holding register, that is HR76, and after doing the addition operation, the result will be stored in HR77. So in arithmetic operations, a HR might contain the first operand, another HR the second operand, and a final HR the destination of the mathematical manipulation. Then in timer application also we will see the huge application of holding registers. Here you see the two registers are present in a timer application. One is for preset. So preset is where the timing value is set. It may be a constant or a designated register. Means this preset value, it is 14. The timing operation is for 14 seconds, which is written in a holding registers. And also another registers you can see HR101. This register is designated register in which the count takes place. In the timer function, the preset value would be placed in a constant or designated register, and the HR is the register in which the count takes place. Here another one important thing is that this preset value may be constant, which is written in a holding registers, or preset value can be a designated register. Means suppose the preset value has to be read from a registered content. So that also possible in case of timer. That we will see when we will discuss about the timer operation. And the counter application. So in counter application also we can see that one preset value is there. The preset is where the count value is set. It may be a constant or a designated registers, and register HR102, another register is required where the count take place. The counter application, the preset value is also placed in a constant or designated register. The HR is the register in which count take place. So now we are going to discuss about the input register and output register. So input register may be single or group. Output registers also may be single or group. So the input register has basically the same characteristics as the holding register, except that it is readily accessible to the input module terminal port. The number of input registers in a PLC is normally 1/10 of the holding registers. The input group registers is somewhat like the input registers. It differs in that each one of the individual 16 bits is directly accessible from one input port. One input group registers receive data from 16 consecutive input ports or terminal. Without the IG system, we would need 16 registers to service 16 inputs. The input, which will be clear actually when we will see the figure. The input module port or terminal corresponds to a single group register bit. Each input group register status controls one bit status. When a port is enabled or on, it creates a 1 in the corresponding bit slot. If the port is off, it produces a 0 in the corresponding bit slot. So this is the pictorial representation of the input group register. So you see the input terminal from 1 to 16 is stored in an input group registers, and the status of the inputs, if some status are some inputs are on, it will be designated by 1, and if some input is off, it will be designated by 0. Okay, so this is the work of the input. So like that, the input group registers will be there. So this is the input group register IZ001. So it having 16-bit, it is a 16-bit registers, and it is going to store the status of 16 inputs simultaneously. So like that, IG002, which is for 17 to 32, 33 to 34, 48 may be IG03, and 49 to 64 may be IG04. So now the output registers, which may be single and group. Like the input registers, the output register has the same basic characteristics as the holding registers. The output register differs from the HR, however, in that it is readily accessible to the output module's terminal and ports. The number of output registers is normally equal to the number of input registers. The output group registers is organized in a manner similar to the input group register. So one OG register can control 16 outputs. If a 1 is in a bit position, it will turn the bit's corresponding output on. A 0 will turn its corresponding output off. So this is the pictorial representation where you can see that several HR are there, that is holding registers are there. So this status of the holding registers are going to transfer to the corresponding output group registers to activate the outputs. So here you can see that HR276, whatever the contents, so how this HR276 are calculated by some logical operation or mathematical operation, that we are going to learn. So suppose by some mathematical operation or logical operations, the HR276 having this bit content, 16-bit register content, you can see, which is going to transfer to the OG2, that is where with this OG2 actually physically the outputs are connected, and based on the status of the OG2, the outputs of the PLC is going to be either activated or deactivated. If certain content of the register bit is 1, it is going to be on. If something is 0, then that corresponding output is going to be off. So like that, several OG1, OG2, OG3 will be there. All are 16-bit long. So with this, I will end here, and next class we will discuss about the timer application of PLC. Thank you.